All right, so we'll quickly go through these questions from Friday, okay? And then we will move on to naming compounds today. We'll be doing that again tomorrow, most likely also on Wednesday, okay? Possibly Thursday, and then Friday. I'm hoping if we haven't moved on by Thursday, we'll certainly be moving on by Friday to other things, okay? The idea of the atom was first proposed by whom? Democritus, right? Okay, Democritus was the Greek thinker who thought that everything could be made up of these little uncuttable, particles that he called atomos. Okay, why wasn't his idea accepted? Right. Okay, Aristotle's idea of the four elements was more widely accepted because it made sense to people. Okay, they didn't have to imagine tiny invisible particles, okay, that existed everywhere, and they just didn't like that idea. The four elements made way more sense. They could figure out what mixture everything was made out of and all that. So it was far more practical, and since there was nothing to prove either one of them, okay, they went with the one that was simply more practical. All right, second question. What elements did the Greeks believe all matter was made out of? And earth, right, okay? So air, water, fire, and earth, okay, were the four elements that everything was supposedly made out of, okay? And again, it was a logical conclusion because they could look at materials and figure out what parts water, what parts fire they were, okay? And the examples we talked about were like steam, okay, where steam was some parts water and some parts fire and some parts air, okay? Mercury was some parts water and some parts earth, okay, because it was a liquid metal, stuff like that, okay? They were able to figure those things out because it made sense. Number 3, during the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. Who were they? The alchemists, right? The alchemists were those people that were trying to turn lead into gold and find the elixir of life and do all kinds of things that would make them filthy, stinking rich. Okay, obviously they never achieved those goals because we now know you cannot turn the atoms of one element into the atoms of another element. Okay, it is not physically or chemically possible. Okay, number 4, in the late 1700s, a man used the data from many experiments on matter to develop an idea on the structure of matter. Who was he? Oh. John Dalton, okay, was the guy that came up with the atomic theory, and his theory had 4 points. Okay, what was one of the points? Right, atoms of the same element are all identical, same number of protons, electrons, etc. Obviously, he didn't know about those at the time, okay, but we know that now. Okay, atoms of different elements are different. That's why they have different properties. Okay, what else? Seth? Right, everything is made of atoms. Okay, it was essentially the first point. All elements are made of indivisible particles called atoms. Okay, third point, or a third point. Okay, what happens in a chemical reaction? Yep. Right, they are separated, joined, or rearranged is what happens in a chemical reaction. Okay, and the last thing has to do with those whole number ratios and ties in again with atoms not being divisible. What was it? Right. They combine in whole number ratios, okay, but obviously, you can't have like half an atom in a compound, okay? Things of that nature. All right. Everybody with me there? Everyone's good with that? Okay. All right. Next up here. So number 7, as our knowledge increased, we discovered that the atom had smaller parts. Okay, name those parts, describe them, and tell where they are located, according to what we believe to now be true. Okay, the way I would ask this question on a quiz would be draw me a picture of what we think the atom now looks like. All right, so where would you put the protons? In the nucleus, okay, the middle, okay, that's where the protons go. And protons have what kind of a charge? Positive, okay. And then we have the neutrons. Where do they go? They go in the nucleus as well. Protons and neutrons are the heavy parts. They're in the nucleus. Okay, they have no charge. And then the electrons are there. They float around the outside in the cloud. Okay, and they have what charge? Okay, they're negative, right? Okay, number 8. 1 cubic centimeter of lead is much heavier than 1 cubic centimeter of carbon. Why do you suppose this is? Okay, well, if we look at the periodic table, and I will give you guys one today for each of you. Okay, if we look at carbon, okay, carbon has an atomic number of 6. Okay, that means that every atom of carbon has 6 protons. Okay, and it has an atomic mass of about 12 point something, right? 12.0. Okay, so it has 6 neutrons. And it has 6 electrons, because the electrons and protons have to be the same number. All right, that's for carbon, right? But lead's number, okay, is way over here. It's Pb. It's 82. Does it have a little bit more stuff in the nucleus? Yeah, like 10 times as much, more than 10 times as much. Okay, it's got 82 protons, it's got 82 electrons, and it's got an ungodly number of neutrons. Okay, 100 and some neutrons. Okay, so we're looking at obviously a much different, a much bigger atom. All right, so we have the same number of atoms. Okay, then obviously the lead's going to be much heavier. Okay, nuclear reactors. Okay, they use atoms with very large nuclei, like uranium, which has 237 particles in its nucleus. Okay, why wouldn't they use smaller, less dangerous atoms like lithium? Wouldn't make as much power is one reason. Why else? Yeah, it's a lot more difficult to hit a small atom. Okay, small atoms are stable. Right? When you hit them, they're too small to break. They stick together really well. Okay, they're not really. The bigger an atom gets, the harder it is for the electromagnetic forces within it to hold it together. All right, that's why really big atoms tend to be radioactive. Okay, something that's radioactive is always breaking down. It's giving off particles. Okay, as it breaks down, that's what radiation is. And so, the bigger something is, the more likely it is to break when you hit it with something else. That's why we use those big atoms. Okay, they're far easier to break, far more likely to break, and since they're bigger, they also have more energy. All right. Atoms are indivisible. Why was this statement believed for so long, and why is it still somewhat true, provided no human technology is present? Okay, can you cut an atom? No. All right, atoms are too small. All right, they simply don't break apart necessarily on their own. All right, so that's unless there's human technology present where we've got something that can fire subatomic particles at the atom and break it, it isn't going to happen on its own. All right. From what you know of the structure of the atom, why do you think the atom stays intact? Okay. Why do the electrons not fly off or the protons separate from the nucleus? Okay. Yeah, to some extent that would be right. The charges are attracted or attached to the nucleus. The electrons are negatively charged. The nucleus has all the protons, so it's going to seem it's going to seem positive, and so there's this attraction, an electromagnetic attraction between the two. Okay, positive attracted to negative. Okay, and so they tend to stay together. The nucleus stays together because protons are so positive. Okay, that neutrons are attracted to them. All right, and so there's this strong force and this weak force and things like that that keep the atom intact. All right, but it has to do with those differences in charges. Okay, number 12, the same principle that makes glow-in-the-dark materials work is used by plants to produce food. All right, and we talked about how the electron cloud model, or the quantum mechanical model, okay, is used to explain that. The electrons are in this cloud around the outside. When the atom is energized, okay, and certain types of chemicals do this better than others, but when the electrons are energized, they move further away from the nucleus of the atom. All right, and then when that energizing influence is gone, in this case the sun, they begin to move back closer to the nucleus. And when they move closer, they give off all of the energy that they have absorbed. Okay, for a glow-in-the-dark material, that means it gives off the light as light, and it glows in the dark. For a plant, that energy becomes chemical energy in the form of something called adenosine triphosphate, okay, which is used to make other things within the plant. Okay, everybody follow me there? Yeah, okay. All right, so that's all 12. Okay, I would say make sure you go over those tonight. Right, when you are preparing for your quiz, which PS has already been tweeted. Okay, tweeted it this morning. If you haven't checked already, it's already up there. All right, so you know, I think I have 6 questions on there. Okay, that you'll have to answer tomorrow. Okay, and they're all straight out of this and your notes for tomorrow. All right, so what we're going to go over here, guys, okay, writing the names and chemical formula for simple, what we call binary compounds. So they only have 2 parts. Okay, binary means having 2 parts. What we have to be able to do after today, okay, identify whether a compound is ionic or molecular. That should be a review of Science 9 for you, but we'll go over it anyway. Okay, and we should also be able to write formula and proper names for compounds. We may not get through all of them today, but we'll get through a pretty fair portion of them. All right. An ionic compound has what in it? Okay, it has a metal and a nonmetal. Okay, all ionic compounds have one element from both sides of the periodic table. Okay, on your periodic table, you'll notice there's a dividing staircase. Okay, it's about 3/4 of the way across from left to right. Okay, that separates the metals, which are on the left, from the nonmetals, which are on the right. Okay, and so ionic compounds have something from both sides of the periodic table. Okay, everybody with me there? If you are a molecular compound, you have 2 nonmetals, okay, that make up that particular compound. All right, so ionic compounds, okay? Ionic compounds, like we said, they occur when you have a metal and a nonmetal, okay? React to form a new molecule, all right? Naming these is relatively straightforward. You don't require a whole lot of rules or anything like that for writing the name of an ionic compound. You write the name of the metal, and then you write the name of the nonmetal. And you change the nonmetals ending to "ide." All right, so if you have sodium and chlorine going together, you now have sodium chloride. All right, if you have calcium and iodine going together, you have calcium iodide. Okay, if you have something trickier, let's say lithium and oxygen, okay, then you have lithium oxide. Okay, everyone follow me on that? Okay, it's relatively straightforward. There's only a couple that might be a little iffy on where you would stop the name and put in the "ide." Oxygen might be one, phosphorus might be another, sulfide, okay, phosphide, things like that. Okay, just make sure the ending is in "ide" and you're good. All right, just the non-metal. Only the nonmetal ends in "ide." Okay, when you get an ionic compound forming, okay, ionic compounds form because all elements want to have their outer area of their electron cloud full. Okay, why that is, no one's really sure, but they want to have their outside shell full. Okay, so for metals, the quickest way to do that is to drop electrons or get rid of them. Okay, for nonmetals, the quickest way to get a full outer shell is to pick up electrons. All right, so if we're looking at sodium, for example, okay, sodium's number is 11. Okay, so sodium looks like this. In the lower levels of the electron cloud, you typically only see 2 electrons moving about. All right, in the next level, you'll typically see 8 of them moving about. Okay, and then the outer level can hold another 8, but in sodium, there's only 1. Okay, so quicker for sodium to fill that outer shell by dumping 1 electron or finding 7 more to fill it. If it dumps 1 electron, that shell is now gone, agreed? And the shell below it is full. So now it has a full outer shell. Everyone follow? Right? If you're looking at chlorine, chlorine is kind of the exact opposite. All right, so chlorine's got 2 in its first shell, same as sodium. Okay, its next shell is full with 8. Okay, and the shell on top of that has 7 in it. Okay, and it can hold 8. Easier to find somewhere to put 7 or pick up 1? Easier to pick up 1. That's why sodium and chlorine get along so well. Okay, each of them has what the other wants. Okay, chlorine needs an electron. Sodium wants to get rid of 1 electron. They get along really well. That forms an ionic bond. Okay, ionic bonds are kind of weak. Okay, it's going to sound awful from a sociological perspective, but for an ionic compound, once they've found a place to put their electron, they really don't have any use for each other anymore. So they don't stick together very well. Don't personify that in any way. Okay, but they got what they wanted, and so now they split. Okay, there's really nothing there to an ionic bond. It's not a strong bond. That's why typically ionic compounds dissolve easily in water. All right. Once they hit the water, they split, they become charged particles, okay, and they're gone. They're done. Okay, everyone follow me on that? Okay, so that's what happens with an ionic bond. There's this transfer of electrons. Okay, nonmetal always gains, metal always loses an electron. Okay, that's just the way it goes. Question or no? Okay. All right. Now, for the naming, okay, when you're naming an ionic compound, like we said, you write the name of the metal first and the nonmetal second, and then you put an "ide" ending or suffix on the end. All right. So, what we've got here, the example we talked about, we got sodium plus chlorine, okay, gives us sodium chloride, okay, as our compound there. Okay. What if I have a compound, this is sodium chloride here, NaCl. What about this? There's 2 chlorines in that compound. Does that change its name? Actually, no. All right. In an ionic compound, it does not matter how many of each atom there are. It does not change the name. Okay. Here's why. Ionic compounds can only have one possible configuration. All right. When calcium and chlorine go together, it always looks like this. There is no other way for calcium and chlorine to go together. So I don't need to say calcium dichloride, because everyone knows that when calcium and chlorine go together, they go together that way. Okay? The reason they always go together that way? Calcium wants to give away 2 electrons. Chlorine can only pick up 1. So how many chlorines are needed for those 2 electrons? 2. Okay? So if calcium and chlorine want to go together, there's going to need to be 2 chlorines to pick up the 2 electrons calcium wants to get rid of. Okay? So we always have this balancing of charges. You guys remember being taught the swap and drop last year? Or drop and swap, swap and drop, whichever way you were taught it. Okay? That's the reason for it. Okay? Is to make sure that all the charges balance out. We take this 2, we drop and swap it. We take this 1, we put it here. Okay? And we've got CaCl2. Right? That is the only way calcium and chlorine will go together, so you do not require any prefixes. Right? So there'll never be any monos, dis, or tris on an ionic compound. Okay? Everybody with me there? Okay, big thing to remember, and this applies to ionic and molecular compounds. The names of ionic and molecular compounds are not proper names. Okay, it's not like John Smith or Jane Doe. Okay, they are not proper names. Thus, they are not capitalized unless you are beginning a sentence with them. Okay, the rest of the time they are a form of nomenclature as opposed to a proper name, so they are not capitalized. Everybody follow me there? Really important when you're writing quizzes and things like that they don't get capitalized, right? Because if they are capitalized, they are wrong. Okay, unless you are starting a sentence with them. Sodium chloride is table salt, then you would have to capitalize the S, okay, on sodium. No. Oh, he's already got it. You guys already had? Okay. All right. So looking at this one here, okay, we've got aluminum reacting with chlorine, and that gives us this compound here. AlCl3. I'm not concerned with the 3. This stuff is simply called aluminum chloride. Okay? Reason it's called that, this is the only way that those two things can go together. Okay? Because when we drop and swap, you get 3 and 1. Right? It's the only way aluminum and chlorine will go together. Right? So it eliminates the need for those extra prefixes. Okay? We do use the prefixes if we're dealing with molecular compounds, but we'll get to that in a minute. Okay? The other thing to remember here, a true compound, a true ionic compound, okay, will have a net charge of 0. That means all the positives are balanced by all the negatives. Okay? And again, that's why we do this drop and swap thing that you learned last year. Okay, I've got an aluminum that has a charge of +3, and I've got chlorine that has a charge of -1. If I want this thing to have a charge of 0, how many chlorines do I need to balance off the 3 positives on the aluminum? Every chlorine can pick up 1 positive charge. Okay, so how many chlorines do I need? 3. Okay, that's why we do the drop and swap. Okay, everyone follow me there? If I take this and I say, now I have 3 of these, 3 times -1 is -3. Does that balance this? There's only 1 of this. 1 times +3 is +3. +3 and -3 is 0. Now that compound has a charge of 0. Okay, you can always check if you've made the compound's formula right, okay, by checking to see if the charges work out to 0. Right? All right. How do we know what the charge on everything is? It's on your periodic table. Okay, in the top, I believe, right-hand corner of all of your periodic tables, okay, the charge is written in there. And it's not in the very top right. It's kind of, there's one line of numbers, and then the charge is underneath that. Okay. All right. There are some special cases. If you're looking at your periodic table right now, you'll see that some of the metals have more than 1 possible charge. Okay, things like iron has a 2 and a 3 listed there. +2 and +3. Okay, cobalt, similar. It's got a 2 and a 3. Copper's got a 1 and a 2. Right? Lead's got a 2 and a 3 or a 2 and a 4. Okay, so there's lots of them there that have more than 1 possible charge. We have to have some way of telling compounds apart. Okay, so here's what we got to look at. This compound here would be called iron oxide, right? It's iron and oxygen. What would you call that? Well, except that we don't use prefixes in ionic compounds. And this is still an ionic compound. That's the trick. Both of those would be called iron oxide. Is that a problem? Actually, it is. One of them's poisonous, one of them's rust. Okay, so you write down, add this many grams of iron oxide to your food to increase your hemoglobin or something like that, and someone adds the wrong stuff and they die. Is it your fault? Okay, you got to tell them which iron oxide it is. Hopefully, no one would be that dumb and no one would add iron oxide period to their food. But okay, it's kind of an extreme example. Okay, obviously both of those compounds have different properties. They're not the same thing. We have to have a way of telling them apart. All right, so what we do is we use a Roman numeral to tell people which iron we used. Did we use the iron with the 2+ charge, or did we use the iron with the 3+ charge? Okay, everybody with me so far? All right, so sometimes in a name of an ionic compound, you'll add a Roman numeral. You will only add that Roman numeral if the compound you're dealing with has a what we call multivalent metal. That's one of the metals that has more than 1 charge in it. Okay, everyone following me? Okay, so here's what we do. We got to figure out from this compound, from this formula, which iron this is. Is it the 2+ iron or is it the 3+ iron? Well, does oxygen have more than 1 possible charge? Check on your periodic table. The only charge listed next to oxygen is -2. All right, that's what I go by then. Okay, if oxygen's always -2, and all ionic compounds have to work out to have a charge of 0, what's the charge on this iron? 2. Because if it's 3, it doesn't work. Okay, I'd have a net charge of +1. That can't happen. All right, so I always look to my non-metal to tell me what the charge on my metal is if the metal has more than 1. All right, so in this case, this has to be iron 2 oxide. All right, now it's a little trickier with this one, but it's the same idea. Oxygen is always -2. How many oxygens are there in this compound here? 3. Right? There's 3 oxygens here. That's what O3 means. Agreed? All right. If every oxygen has a charge of -2, and there are 3 of them, how many negative charges are in this compound? 6. All right. So there's 6 negatives in this compound. I need it to come out to 0, so I need to have a charge from the irons of +6. I have 2 irons to do that with. So each iron must have a charge of 3. Okay, because 2 times +3 would give me +6. Okay, so this is iron 3. So that stuff there would have this name. Okay, it would be iron 3 oxide. All right, that's probably new. You probably didn't learn that in Science 9. That's something new for naming. Okay, you're going to get lots of time to practice that here over the next couple of days. All right. So, big rules to remember for ionic compounds. Metal gets named first, non-metal named second, non-metal ends in "-ide", never capitalized. Yes, the Roman numeral should go in brackets generally. Okay. Okay, I want you guys to try, let's say, the first 5 in this list here. Stop when you get to the 5th one. We'll go through the first 5, make sure we're all doing it right, and then we can do the rest after. I just don't want anyone to practice doing it wrong, okay, past 5. All right, so do up to number 5 and then stop there. I'll give you a few minutes and we'll go through them. All right, let's have a look at the first 5 here, guys. If you're not done the first 5, it's fine. We're just going to go through them here just to make sure everyone understands. All right, so on our first one here, okay, we've got binary ionic compound starting with sodium. Okay, so sodium chloride. All right, relatively straightforward. Again, no capital letters. It's not a proper name. All right, for our second one, we've got K and F. K stands for potassium. Okay, we always, again, write the metal first, potassium, and then the non-metal, fluoride. Okay, and you can spell fluoride with the U or without it. It doesn't matter. Okay, either way is fine. All right, for our third one, hydrogen and iodine. Now, if you look at hydrogen on your periodic table, you might notice it actually has 2 charges, -1 and +1. It does not, however, require a Roman numeral. Hydrogen, when written first, as it is in this compound, has a positive charge. Okay, it's behaving as a metal. It can also behave as a non-metal. The way you can tell it's behaving as a non-metal is it's listed second. All right, so in this case, this is behaving as the metal, so we don't change its name. We just write it as hydrogen. Okay, and then it's with iodine, so it's iodide. Okay, again, all lowercase. All right, for number 4, Ca stands for calcium. Okay, and bromine, okay, changed to IDE. Does it matter that there's a 2 there? Okay, no. It's an ionic compound. We don't write prefixes on ionic compounds. It's just calcium bromide. All right, and on our last one here, Al is aluminum. Actually, it's now aluminium. I don't know why they changed it. It doesn't make any sense that way, but aluminium. Okay, and At is astatine, so it's aluminum astatide. Okay. None of the ones on this first page will need the Roman numerals, so you don't have to worry about those yet. Okay, we'll go over a few that require the Roman numerals in a little bit. All right, what I'd like you to do now, okay, is try the rest of these. Okay, write the proper names for the rest of those compounds. I'll give you a few more minutes. Okay, so for number 6 here, we got cesium with sulfur. So that's going to look like this: cesium sulfide. Okay, again, no Roman numerals or prefixes required on that one. Okay, for number 7, we've got sodium with oxygen. So that's going to be sodium oxide. Okay, again, only the IDE ending on the nonmetal. For number 8, we got barium and selenium. So that's going to be barium selenide. It could also be selenamide. It doesn't matter which way you write it. Both are acceptable. Okay, it depends on where you decided to end selenium before. All right. For number 9, you got radium and tellurium. Same thing with tellurium as it is with selenium. You may choose to end the word and put the ID in a different spot. Okay, I always write it as radium telluride. It could be telluramide, okay, as well. It doesn't really matter either way. For number 10, we got lithium and fluorine. So lithium fluoride. All right, for number 11, we've got rubidium with sulfur. So that is rubidium sulfide. Okay, for 12, strontium with iodine. So iodide for the end of that. Okay, for number 13, calcium and oxygen. So calcium oxide. And lastly, magnesium and selenium is magnesium selenide or selenamide. Either one is fine. Okay, remember, no capital letters. All right, it is a hard habit to break, but people very often want to write all of these with capital letters. Okay, they're not proper names. Okay, questions on any of those? All right. Now, these ones involve some of those multivalent metals that have more than one possible charge. All right, so I'll go through a couple here with you, okay, to sort of review and outline the procedure, and then you guys can try some. All right, this one we've already done once before, but we'll do it again because it's a good example. Iron has more than one possible charge. It can be a 2+ or it can be a 3+. All right, we have to figure out which one, so we put the right Roman numeral in the name. Since oxygen is always a -2, we can use that to figure out what the charge on the metal is. All right, so every oxygen is -2, and there are 3 oxygens. Okay, so 3 times -2 is -6. All right, if this compound is going to come out neutral, I need 6 positives, and I have to get them from 2 irons. So what times 2 will give me +6? +3. All right, that means the charge on iron is +3. All right, so this is iron, Roman numeral 3, oxide. All right, now, usually at this point, people start to notice a little pattern, and they're like, oh, Mr. Coder, can't I just take this 3? It always seems to be the charge on that metal. It is about 3/4 of the time. However, there are cases where it doesn't work out that way, like this one. Okay, if you just take the 2 off of the oxygen and say that that is lead 2 oxide, you're wrong. Right? Here's why. Lead can be 2 or it can be 4. Oxygen is always -2. 2 times -2 is -4. What's the charge on lead? +4. All right, so don't just reverse your swap and drop. That's only going to work 2 out of 3 or maybe 3 out of 4 times. Okay, and most of the time on a test, I would of course pick the ones it wouldn't work for. All right, so best to do it this way here, okay, with a little bit of math. Okay, it's not hard math, it's just a little bit of math. All right, let's look at number 2 here. I've got cobalt and I've got sulfur. Okay, now cobalt can be a 2 or a 3, right? Those are the possible charges for cobalt. Right? What's the charge always on sulfur? -2. So if sulfur's a -2 here, cobalt has to be +2. All right? And then we write cobalt, Roman numeral 2, sulfide. Okay, you can also write it PHIDE. It's fine either way. Okay. Questions on how that works? All right, I want you guys to try the next 8 there. Okay, give them a try, and then we'll go through them here in a few minutes. All right, so on number 3, I've got Mn, which stands for manganese, along with chlorine. Okay, if there are 4 chlorines, and every chlorine has a charge of -1 according to your periodic table, okay, that gives me a total of 4 negative charges. I only have 1 manganese, so the charge on manganese must be +4. Right, that's the only way to make that come out to 0. So this is manganese, okay, 4. Okay, remember your Roman numerals. IV is 4 because it's 1 before 5. That's what V stands for. Okay, manganese 4 chloride. Okay, if you don't know your Roman numerals, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, you probably won't need past 4 for this, okay, very often. All right, but there they are, up to 10. Okay, for number 4, we've got copper with sulfur. Again, sulfur always has a charge of -2, so this must be the copper with the 2+ charge. So it's copper, Roman numeral 2, okay, sulfide. Okay, for number 5, Sn stands for tin, okay, and it's with tellurium. Tellurium's charge is always -2, I believe. Is that right? Someone just double check real quick. Is it -2? Yeah. Okay, so that means that there are 4 negatives, so this tin must have a charge of +4. So this is tin, IV, okay, telluride. And with number 6, Hg stands for mercury, At is astatine, and astatine's always -1. Okay, so this must be mercury, Roman numeral 2, astatide. All right, I'll give you a couple more minutes to do the last 4, and then we'll go through them together. All right, let's look at the last 4 here. Okay, so PO stands for polonium, okay, and iodine is I, so iodine is always -1, which means there are 4 negatives, so polonium, since there's only 1 of it, must have a +4 charge. Okay, so polonium, okay, IV, iodide. Okay, and for number 8, we've got antimony, that's what Sb is, with sulfur. Sulfur is always -2, 3 times -2 is -6. So I need 6 positives from this antimony, which means each of the antimonies must be +3. So we're looking at antimony, okay, 1, 2, 3, sulfide. And for number 9, we've got nickel and nitrogen together. Nitrogen is always -3. Okay, so there are 6 negative charges here. That means this nickel must have a charge of +2. 3 times +2 is +6. Okay, so nickel, Roman numeral 2, nitride. Okay, and lastly, okay, we've got ruthenium. Okay, ruthenium with oxygen. Okay, oxygen again is always -2, so that must mean that this must be +4. All right, so ruthenium 4, okay, oxide. Okay, questions on those? Takes a little bit of practice with those. The big thing with those guys isn't when you know that you have to do it, it's when I give them to you in a list of other ionic compounds that don't need it. Okay? Will you remember that in that case you need to add Roman numerals to the name? Okay? All right. Being able to name compounds, guys, is probably the most fundamental skill you can have in chemistry. Because if you can't name the compounds correctly, you won't be able to write the reactions we do later on properly, okay? And then it begins to kind of snowball, all right? If you're not getting the first part right, you're not getting the rest of it right, and things get bad in a hurry, all right? So make sure you are practicing your naming, all right? We're going to be working on it tomorrow, be working on it on Wednesday. We'll see if we need to practice it on Thursday as well, okay? But we'll spend some time on it for sure. Okay, the other kind of compounds, molecular compounds. Okay, molecular compounds occur when you have two nonmetals react to form a new substance. They are considerably different than ionic compounds. If you recall, we said that ionic compounds don't really stick together very much because they got what they wanted, they got their electron, or they got rid of their electron, or whatever. Okay, molecular compounds are the exact opposite. They stick like glue to each other, right? Because they don't get to trade electrons, they have to share them. Nonmetals all have negative charges, which means they all require, okay, more electrons. They need to get more electrons to fill their outer shell. The only way to do that with another nonmetal that also requires electrons is to share. All right. So if we're looking at something like water, okay, and that's what you see here in this picture here, okay, water is two hydrogens, these green ones, okay, and one oxygen atom. Oxygen wants to have 8 electrons in its outer shell, but it only has 6. So if it meets up with 2 other hydrogens, those hydrogens provide the extra, okay, electron or electrons that oxygen needs. But hydrogen also wants to have a full outer shell, and the only way for it to do that is for it to also have an additional electron. Well, if they share these outer electrons, they both get to have full outer shells, but they only have those full outer shells if they stay together. Right? So these compounds tend to be a lot stronger, okay, than an ionic compound, and as a result, they have a lot different properties. They tend to be less crystalline. They tend to be less soluble in water, okay, and they do a lot of strange things that ionic compounds don't generally do. Okay, so something to keep in mind there. Okay, you can see here this is an ionic compound. Okay, electron on each atom. Okay, but in a covalent or molecular bond, the electrons are shared. Okay, and so they have to stick together quite a bit harder. All right, for the naming parts. When you're naming molecular compounds, now you have to use prefixes, right? Because there isn't going to be a balancing of charges. The two things that are going together are both negative, and two negatives don't make a positive. All right? There's no way to balance a negative charge by putting more negatives in with it. Agreed? Okay, so that's not going to work. You're not going to be doing any swapping and dropping here. All right? As a result of that, when I put any two nonmetals together, there's really any number of combinations that they could take. All right? When I put carbon and oxygen together, for example, I could get this. I can get this. Okay? I can get any number of things. All right? I have to be able to tell them apart. I can't say that this is carbon oxide and carbon oxide. They're not the same thing. All right? So instead, this is carbon monoxide, the poisonous stuff. Okay? And this is carbon dioxide, also poisonous, but not in the same way. All right, everybody follow me? All right, so in these we use prefixes. Okay, so we use prefixes to denote the number, right, of atoms of each element involved. The only exception is if the first element, there's only one of it. Okay, you'll notice that in both of those compounds it was carbon monoxide, carbon dioxide. In neither one of those did I say monocarbon monoxide, just carbon. All right, so I only apply everything other than di, okay, up from there for these ones. Okay, so examples here. This is carbon disulfide. Okay, this stuff here, dinitrogen, and that should be, that's a typo, dinitrogen monoxide. All right, they both get prefixes if it's anything other than 2. Okay. Now, the prefixes, in case you don't know them, you should probably write them down because you don't have them anywhere. All right. 1 is mono, 2 is di, 3 is tri, 4 is tetra. They're pretty much like all the shapes. Okay. 5 is penta, 6 is hexa. 7 is hepta. Don't use septa. Some people might tell you septa is okay. Mr. Real, who teaches Chem 20, will kill you if you use septa. He hates it. I don't know why. Just got a thing. Okay? Don't use septa. Gets him really mad. Okay? 8, octa. Okay? 9 is nona. 10 is deca. You shouldn't need anything beyond deca, okay, for our purposes. All right, so naming these is pretty easy. Write the names of the things and put the prefixes on. All right, again, your second nonmetal, the second thing in the compound, ends in what? Ide. Okay, chemicals always end in ide. Okay, so we're going to make sure that our second thing ends in ide. All right, the example we have up here, okay, P4O10 is tetraphosphorus decaoxide. So the first thing, you write the name as it appears on the periodic table. The second thing, you write it with an ide ending and any prefixes that it requires. All right, let's have you try, let's say, the first 5 of these. Okay, we'll do the first 5 of these, and then we'll see how we're doing on those. Okay, don't go beyond 5 just in case you're doing it wrong. Okay, let's look over those first 5 here. All right, so on this one here, I've got nitrogen and iodine together. Okay, so nitrogen, and again, I don't change the name of the first elements. Okay, triiodide. Oh, iodide. Okay. All right, for number 2, I've got carbon and iodine. Again, there's only one carbon, so I don't need to put mono on the first one. So this is just carbon iodide. Carbon tetraiodide. Okay, we do need a prefix on the second one, tetraiodide. You don't need the hyphen. Okay. Right, number 3, I've got nitrogen and oxygen, and I've got 2 nitrogens. Do I need to put a prefix on nitrogen now? Yes. All right, so this is dinitrogen trioxide. All right, for number 4, I've only got 1 tellurium, so I don't need any prefixes. Okay, tellurium diastatide. Okay, and then for number 5, I've got 2 phosphorus, so I need a prefix, diphosphorus. Okay, trisulfide. Okay, is that making sense to people? Okay, again, we're going to get lots of practice on this over the next little while. Okay, we'll leave it at that for today. I'm going to hand out your report cards here in just a sec. Okay, and then obviously tonight, make sure you check the quiz that I tweeted this morning. Okay, do those questions, look up the answers so you've got them ready for tomorrow.